Feynman describes it in his book, 1965 book, The Character of Physical Law, and he mentioned it also in his lectures on physics. The idea is very simple, a bit too simple for some people, and the idea is that you have lots of particles flying around and they hit masses, field quanta flying around, hitting particles, pushing them together. Problem with this, there's several problems. So Feynman, let's deal with his idea of the problems with it first. And his idea basically is drag. If you have a particle hitting a mass that's moving, so Feynman has a problem with a moving mass. If the mass is moving, you get more particles hitting it from the front than the back, and it will slow it down. The planet will instead slow down and it will spiral into the sun, so there'll be a sideways force acting on the planet, pushing it inwards to the sun, and it will end up falling into the sun, and it won't have lasted all the time it has lasted. There are other variations on the same problem. They're assuming a real gas, they're assuming an ether, which of course doesn't exist. What you have to do is you have to have an environment in which there's a pressure, some kind of pressure carried by some kind of quantum field. Field quanta flying around, hitting particles, pushing them together. For you to get this kind of problem for everything, but we know there is radiation in the vacuum. We know that from the Casimir effect. And now the Casimir effect, you can have two parallel conducting metal plates, and they get pushed together because between the plates the distance is too small to allow long wavelengths to exist, and therefore they don't exist between the plates, but they exist on the outside of the plates, so the plates get pushed together. It's the Lesage mechanism, which is the mainstream explanation for the Casimir effect. Gravitation, you've got the problem. Why do all similar charges attract, whereas in electromagnetism all similar charges repel? The string theorist, simple answer, you need spin 2. Now in electromagnetism you have spin 1, gauge bosons being exchanged. This idea that from 1939, that gravitational waves are composed of gravitons, field quanta with spin of 2. The idea of a spin of 2 is that there's apparent universal attraction, but you have a U1 an Abelian gauge group, a very simple gauge group. There's one element in it, and that's the U1 hypercharge in the standard model. After mixing with the neutral massless particle of SU2 gauge boson there, you get the mixed result, which is supposedly the photon of electromagnetism. The problem Feynman had with this Lesage mechanism was that particles will slow down moving objects. Now, clearly Feynman, I don't know how he was justifying that with the Casimir force. He was just ignoring the Casimir force. Does he think that disproves the notion of a gauge theory? Because the gauge theory says there are particles moving in space. They're being exchanged between particles moving force. If that's, if it's a case that any moving body is going to have a drag because it's going to be hitting more gauge bosons for electromagnetism, for the Casimir force from the front than from behind when it's moving along, then you can disprove the standard explanation for the Casimir force, because the metal plates, if they're moving, on one side they're going to be hitting more gauge boson, on the other side they're going to be hitting less. Mainstream quantum spin 2 graviton idea is wrong. The reason being that if you look at the mainstream quantum spin 2 quantum gravity idea, what they're saying is that gravitons are only exchanged between two particles, two masses. It's a non-holistic approach. There's quackery in modern physics, and it's a foundation of modern physics, is quackery, a misinterpretation of what Einstein said in 1985, all this other things, a religion. But that's not the point I'm making. Let's get back to quantum gravity again. Feynman says, you have a problem, you move and you experience more gauge bosons from the front and it slows you down. Well, Fitzgerald would say you move and you experience more gauge bosons from the front, and it doesn't slow you down so much as it increases your inertial mass. There's a Fitzgerald-Lorentz transformation. Your mass goes up particularly as you start to move with the velocity of, relativistic velocity, in other words, your velocity approaches the velocity of the Field quanta, you get an effect analogous to a shock wave in air. You start to move a plane near the speed of sound, you're going almost at the speed the air molecules are going, you get a shock wave, and that slows so of course a huge amount of drag on the plane because you're creating supersonic waves around you. It slows the plane down, it causes drag. But you don't get drag from gauge bosons. What you get instead is an increase in inertial mass. You get a lengthways contraction because of the pressure head on. So you get effects, but they're not the drag effect and the heating effect that Feynman and other guys like Lord Kelvin assumed to be the case. In 1996, we came up with an idea that there's an acceleration in the universe. Outward acceleration, magnitude being approximately the Hubble constant multiplied by the velocity of light. Acceleration about 6 times 10 to the minus 10 meters per second squared. This was observed observationally by Saul Perlmutter and others using CCD telescopes about 2 years later. I tried to get this published at the time, no one was interested, seemed too small an acceleration to detect, blah 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 blah. No one was really interested in the theory, no one was interested in the prediction, and it's continued even after the prediction was confirmed, still no one's interested in it. Anyway, the idea in a nutshell is that the mainstream quantum spin 2 graviton idea is wrong. The reason being that if you look at the mainstream quantum spin 2 quantum gravity idea, what they're saying is that gravitons are only exchanged between two particles, two masses. It's a non-holistic approach. But in this particular example, all gravitational charges will be exchanging gravitons in the universe. And the amount of mass between the apple and the Earth is insignificant compared to the masses around us. Now, if they're exchanging gravitons, the apple and the Earth exchanging gravitons to the rest of the mass in the universe, the gravitons which are coming inwards to be received by the apple and the Earth are converging inwards from an isotropic distribution of mass around us in huge quantities of stars in every direction, galaxies, supernovas, all kinds of black holes, all kinds of mass out there. A huge amount of mass, and these gravitons are coming and converging towards us. So, if you try to include them in your calculation, you no longer get, if there's two masses, you assume there's no other masses, there's two masses in the universe. To get gravity, because you have the attraction of light charges for gravitation, gravitational charges, mass energy. These are attracted together. We know that there's universal attraction. No one's ever seen over a short range in a laboratory masses being repelled, although of course in the universe there is cosmological acceleration outwards, so that kind of looks like a repulsion over very, very long distances over between very, very large masses. There seems to become some kind of repulsion force, and that's the mainstream interpret that as being a cosmological constant effect, a dark energy. I've got something to say about that in just a moment, but if we just get to the question of what field quanta causes gravitation, if there's a field quantum theory of gravity, it's not going to be spin 2 field quanta if there's a lot of mass surrounding your two masses there, because if you have two masses, Earth and apple, and there's nothing else in the universe, then the gravitons will only be exchanged between them. And it's quite true. Z gives a pretty good explanation in his book. Assuming that that's the case, assuming that you can ignore all the surrounding masses in the universe, all the 99.9999% of all the masses, all the mass in the universe is that surrounding you. It's not the mass of the apple, it's not the mass of the Earth, it's not the combined mass of apple and Earth. It's the surrounding clusters of galaxies which are contributing the mass. So you've got to include that. Or at least I claim you've got to include that. Other people think you can. They all think it from Pauli and Bridge in 1939 onwards, they all believe that you can ignore that and you just do a path integral or some quantum field theory calculation for gravitation between two masses. It proves you need to have a spin 2 field quanta. Now another aspect of this sort of argument is it's a very weak and tame argument, and it's a completely false argument. But they built string theory on this because string theory includes a mode for spin 2 field quanta, so it could theoretically contain a theory of quantum gravity. They don't have a theory of quantum gravity. They've got a landscape of 10 to the 500 different theories, but potentially one of those could be a theory of quantum gravity if they could pick it out from the cosmological landscape. They've got 6 extra compactified dimensions in string theory, and they don't know, because it's supposed to be at the Planck scale, that you can't have any parameters for any of those particles, so there's a huge number of variations in the possible string theory framework for making specific predictions. So it's a very weak theory, it's a very vague theory, it's compatible with almost anything, probably excluding the real theory, because the real theory is, as I say, inconsistent with spin 2 gravitons. We have is your spin 1 gravitons. If you're going to exchange field quanta with all the particles in the universe, the exchange field quanta are going to, by analogy to the Casimir effect, where you have two metal plates, conducting plates, being pushed together by the exclusion of longer wavelengths than the order of magnitude of the gap between the plates. They're being pushed together because you have a smaller energy density between the plates, because it's excluded wavelengths, excluded long wavelengths. The fundamental particles inside an apple are getting pushed down to the earth because there's a smaller exchange of gravitons between the apple and the earth than there is between the apple and the sky, the clusters of galaxies in the sky above the apple and the clusters of galaxies in the sky below the earth. So the apple gets pushed down. The bigger the earth, the higher the acceleration with which the apple gets pushed down, because the greater the fraction of the upwards going gravitons that is being cancelled out by interacting with the earth. If you double the mass of the earth, you have twice as much cancellation. We're dealing with a theory in which only a exceedingly small fraction of the total number of gravitons is actually being shielded by anything in a practical within the solar system. Perhaps if you have a black hole, a large black hole, it will be a much more effective source of shielding. And if you have a cluster of black holes, perhaps you can get up to the extent of mutual shadowing, where the whole thing breaks down and you have add more black holes and there's no more gravitational field because they're already fully shielding it. But the size of a fundamental particle is its black hole event horizon size, which is for an electron 10 to 22 times smaller than the Planck scale, the Planck length. So it's a more fundamental and smaller size than even the Planck scale, extremely tiny size. So you have an enormous amount of mass necessary to completely block gravitons. The Earth only stops a minute fraction of it. The total force coming inwards is equal to total force going outwards. We know that the cosmological acceleration, about 7 times 10 to the minus 10 meters per second squared, multiply that by the mass of the universe, that gives you the outward radial force 10 to the 43 newtons. Newton's third law of motion predicts the equal and opposite force, an inward force of gravitons, a Lesage pressure gravitons pushing inwards, the same magnitude, 10 to the 43 newtons. It's an immense inward force. Only a tiny fraction of that actually becomes gravitation, because the cross-sectional area, the black hole event horizon size for the fundamental particle is so small. So that's how quantum gravity works. Thank you. Bye-bye.